This is somewhat of an exciting topic because bin calculations really set the stage for a more holistic calculation approach. And for the whole rest of the semester, we're going to be doing bin calculations for the different systems that are still left for us to talk about. So bin calculations. So far on our homework assignments, we've really just been looking at single operating point conditions. So in a homework problem, I might have you calculate, well, if this is your cooling load and this is your cooling efficiency, what kW does that take? And then I give you a very simple example of, well, if it operates at this condition for 500 hours a year, how much energy is that? So that would be a single operating point. And that's important to know how to do that, but that's not very useful in terms of the big picture, which is really what we're going to get into now. We're going to start looking at the big picture for all operating hours in a given year, because that's generally how energy savings calculations are expressed. How much energy am I going to save per year? And the resulting dollars as well. So remember how energy engineers think. Energy is used all the time. We don't think like design engineers. We need to think about every hour of the year. So every hour that that device, whether it's a fan or a pump, heating system, cooling system, every hour that that is on, we need to be able to predict how much energy that's going to use. And that's going to change based on variables. If it's 100 degrees outside, an air conditioner will use some amount of power. If it's 80 degrees outside, it's going to use a different amount of power. So the best option, and when I say best, I really mean the most accurate option, is to do a full building energy model, where you build out the entire building, all of the systems within that building, and then you run a simulation. And then the model will spit out a value to you and say, this model that you've created, we are estimating that it uses this much electricity and this much gas per year. Unfortunately, full building energy modeling is outside of the scope of this course. I mean, a whole semester could be on energy modeling. So yeah, the full building energy modeling, that takes a long time. It takes a lot to just learn how to do even the basics of that. And so that's where these bin calculations come in. They're a much faster alternative, and they're only Excel based. Bin calcs, where these really shine, where they're the most useful, is when the energy use or the power draw of some piece of equipment is highly correlated to some variable that we can measure with pretty high certainty. Most often, this is going to be outside air temperature, because we know our heating and our cooling loads are highly correlated to outside air temperature. If it's hot outside, that means we have a high cooling load and a low heating load, and vice versa. If it's cold, we have a high heating load and a low cooling load. If we have a VAV system, then we can predict what our fan speed is going to be. So if it's hot outside, that means high cooling load, which means our fan will be running at a higher speed. And on the opposite end, when it's colder outside, low cooling load means low fan speed. And so because outside air temperature is an easily measurable variable, we can use that to predict how this equipment's going to operate at varying conditions. So the general steps here, and this will make more sense here in a few minutes. The general outline of what we're doing with a bin calculation is we want to determine what is the operating power at each operating condition. So when it's 100 degrees outside, what's our power draw? When it's 95 degrees outside, what's our power draw? And etc. All the way down to the lower temperatures. So for electricity, the operating power that we're trying to arrive at almost always is going to be kW. If we're talking about gas, if it's a heating system, then we need to figure out how much BTU per hour the system's going to use at each operating condition. And if we have the operating power, multiply that by the run hours per year at each of those operating conditions. So if we know every year there are about 100 hours when we're at 70 degrees outside, well, then we know the run hours per year at that condition. So we take that power, multiply by the run hours, we get the energy, whether that's in electricity with kilowatt hours or with gas with BTUs, or probably more often it's going to be therms, because that's typically how utilities bill. And then you sum the total to get the annual usage. So that's a lot of words that probably doesn't make a lot of sense. So let's look at it in a different way. Here's a generic bin calculation. So the idea is we have over here on the far left, these are our outside air temperature bins. And that's where the term bin calculation comes from. So we have each of these 5-degree Fahrenheit buckets. So you can see it's going from 100 degrees to 95, and then 95 to 90, 90 to 85, and then it's going to go all the way down. I'm showing a break in the data here, all the way down to potentially 5 to 0. So those are the different buckets, which represent the different operating conditions. And then we have, well, how many hours are we at that condition? So 20 hours of the year, we are somewhere in the range of 95 to 100 degrees. And then 75 hours per year, we're in this range, and so on and so on. And what you'll probably notice if you look at this data is we're going to have relatively few hours at this peak condition. The bulk of our operating hours are going to be in the more milder conditions. Same on the heating side. Less hours in the extreme, and then as we go up, we're going to have more and more hours in those more moderate conditions. And then this XYZ columns, that's just the calculation steps. And that's going to be unique to whatever system we're looking at. But the idea is you're going to have some set of calculation steps to ultimately arrive at some power. So how much power does this equipment draw at each of these conditions? So when it's 95 to 100 degrees outside, that's going to take some amount of power to run. When it's 95 to 90 degrees, that'll take some different level of power all the way down. And then you get to total energy at the end, which we know is just power times run hours. So if we know the power, we know the hours, we can figure out how many kilowatt hours would be used in this bin. And the same thing for the next bin. And then you go all the way down to arrive at some total at the end. If we were to look at a gas heating example, it's effectively the same thing. So we have our outside air temperature bins, again, separated into 5-degree buckets. The run hours at each condition, some set of calculation steps, but in this case, we're trying to solve for some gas rate. How much gas are we using at each of these conditions? And so if we get to that gas rate, we figure out, well, how many BTUs per hour are we using at each of these temperature conditions? And then we can use this rate multiplied by this number of hours per year to arrive at some total energy use in BTUs, or more likely therms. To use a little bit more of a concrete example, if we were trying to model a cooling system. So we have the same bins over here and the same number of hours. And let's say we calculate a cooling load. Well, we know that when it's really hot outside, our cooling load will be high, but then as it gets colder outside, our cooling load is also going to decrease until at some point in the middle here, you're going to have no load. And then once you get into these single digit temperatures, I mean, you're really not going to have any cooling load at all. So if you can calculate your cooling load, and then we need to figure out some way to calculate our cooling efficiency. And we know that air conditioners operate a little bit better when it's a little bit colder outside. And so this is the one cooling metric where a higher value is worse. Normally, a high EER, for example, would indicate a more efficient unit. With kW per ton, a lower value is better because it's less power per ton of cooling. And so we'll have some calculation methodology to figure out what that efficiency change will be for each of these different conditions. And so we can see, well, we do get a little bit more efficient as we get a little cooler outside. If you know your tons and you know your kW per ton, you can probably see why this is a pretty useful metric now, because if you just multiply those values together, you get kW. And now we can see when it's really hot outside, we're using 250 kW. Whenever this air conditioner is running, when it gets a little cooler, we have less load and we're a little more efficient. So we're going to use a little less power, and so on and so on. And then our total energy, again, we know the kW, we know the hours, that gives us kilowatt hours. Heating example, largely the same. So we have our heating load, which is going to be very high when it's cold outside, and then it'll get steadily lower as it gets a little bit warmer. We'll have some heating efficiency. I think in most of the examples I have you work through, I just have you assume the heating efficiency is a constant value. But you could have an instance where it's not constant, and you're going to have a little bit of a derate in efficiency as you get a little warmer. And then if you take your load, divide by your efficiency, here's your heating input. So this is analogous to our heating power. So every hour that this heating system is running, this is how much power it's using at this condition. Input times your hours, convert to therms, and now you have a unit of energy you can actually do something useful with. And again, this kind of illustrates that at these extreme conditions, even though the input is the largest, because we have less run hours, it ends up being less energy because we just don't have as many hours at those extreme conditions. If you had a VAV system and you were trying to model the fan power. So if we look at fan speed, in a VAV system, your fan speed is maxed out at your greatest cooling load, which would be at the top of your bin calc here. And then it will steadily decrease as the cooling load becomes less, but it does have a limit. We can't shut the fan off entirely. So at some point, we'd have to set up our formula to say, well, below a certain threshold, don't go below 50% fan speed. And then from the fan laws, if we take our fan speed cubed, because that's how our horsepower is going to change, which we talked about in last lecture. And then if we take our base fan kW, so I'm saying at 100% speed, we're at 10 kW. And so if we take that 10 kW, multiply it by our fan speed cubed, we can arrive at an estimated fan power for each of these conditions. And you can see that drops off pretty quick to a pretty low value. And again, we know power, we know hours, that gives us our energy. And that's the basics of a bin calc. In the homework, I walk you through the steps pretty explicitly, but it's kind of fun to go through these, or at least in years past, I've had some students say this is where they started to enjoy the homework a little bit more. They like working in Excel. There's a little bit of a programming feel to it in writing your formulas. With bin calcs, we're typically going to run two different conditions. So we have our baseline. What's it doing right now? So this is trying to mimic the systems as they exist today. So that's part of the equation. And then what is our proposed condition? So what's going to be different? Maybe you're going from a constant volume fan to a variable volume fan. And so you'd have one bin calc where your fan energy is constant, and then you have a second bin calc where your fan energy changes based on a VAV operation. And so if you know the baseline operation and the proposed operation, then the energy savings is going to be the delta. What did it use before versus what is it going to use now? So where do you get bin hours from? There are there's numerous softwares out there that can help generate a bin hour profile. I haven't found one that is free, unfortunately. So you won't be able to do this on your own. So for the homeworks, I'm going to give you the bin hours, but I'll run through an example of what this software might look like. And it's pretty simple software, so I don't think you're missing too much. If you can get your hands on hourly data, which that data does exist, where it will lay out all 8,760 hours in a given year for a given location, and then an associated set of weather data for every hour that exists in that data set. If you have that, you can generate the bin data yourself. And you can also do bin hours based on some other conditions. So maybe dry bulb outside air temperature is not the right variable to weigh against. Maybe you have a system that cares more about the wet bulb temperature, which would be the case if you have a cooling tower, which we're going to get into in a few lectures. Or maybe dew point is important. It just depends on what makes sense. But most often, it's going to just be dry bulb outside air temperature. That's the most common variable that's going to be used with a bin calc. You can do larger bins, so you could do 10-degree increments. So instead of going from 100 to 95 degrees, you go from 100 to 90 and then 90 to 80, or you can do smaller increments and go down to 2 degrees. And if you build your spreadsheets correctly, meaning you write your formulas in a way that you can just copy them down the rows, which is how you should be doing it, then going to 2-degree increments really doesn't change any of the work. It just gives you more rows that you have to copy down. So generally 5 degrees tends to be the most commonly used one, but if you wanted a little more granularity, you could go down to 2-degree increments. Here's an example of one software called SciCalc that can be used to generate bin data. So there's a lot going on in here, but the most important things are up here in the top left. We get to select our location. So in this case, I selected Seattle. And then we can tell it what data do we want to bin on. So I said, I want dry bulb outside air temperature, and then I want it in 5-degree increments. Then we can select the months that we want to pull hours from. So maybe I want to exclude August and September because the building I'm looking at isn't open in those months. Maybe it's a school, and I don't want to overstate savings, so I'm just going to exclude those months entirely. And then I get to pick which hours of which days I want to include. So this would be 7 to 5 p.m., Monday through Friday. So that would be typical for an office building. If it was a school, maybe I'd do 7 a.m. to 3 p.m. Maybe if my building is used on the weekends, I'd include some Saturday and Sunday hours, but I get to choose. And then this little yellow box down here will be updating as I'm checking months and checking hours of the day. It will tell me how many hours I'm capturing in this bin data set that I'm trying to produce. So in this case, it's about 2,400 hours. And in a year, there are 8,760 hours in a given year. So I'm right at about a quarter to a third. So then I set all that up, click create bins, and then this is what it spits out. So I have my midpoint. So this 87.5, this would be the bin for 85 to 90, and we only got 1 hour at that condition. And then it just goes down by 5 degrees all the way down. And again, you can see not a lot of hours at the extreme. So only 1 hour at the top, 5 hours at the bottom, and then it really grows in hours. So the bulk of our hours are going to be right here somewhere in the middle. So that's where the bulk of our energy use is going to be. And as a design engineer, I don't really care about all these hours in the middle because I care about the worst case conditions. But as an energy engineer, this part of the data is very important. So yeah, so you have your bins, you have your hours, and they still give you some other data here. And so these would be considered averages. So for let's say for this 82.5-degree midpoint, we have 19 hours there. Of those 19 data points, the average wet bulb would have been 63.79, and the average humidity ratio would be this. But we've chosen to prioritize our bins based on the dry bulb temperature. And so between two different hours that have the same dry bulb temperature, you could have wildly different wet bulb temperatures for some reason. And if I so choose, I could instead bin on any of these other values if I wanted to. So you don't get to pull data yourself, but ultimately it's not super exciting. Some pros of bin calcs. I mentioned earlier, these are really useful for anything that can be predicted based on some other variable. Most often that's dry bulb outside air temperature. And it's generally pretty simple to set up the spreadsheet. Now, when you start doing these, you might take issue with my statement here saying it's simple. After you've done them for a while, you start to become pretty natural at making them. Your first time through it will probably be a little rough. But once you're kind of over that hump, They are pretty easy to set up and to follow the logic of what's going on in your calculation. And once you have some templates, it can be pretty easy to just plug in some new variables, assuming you've set up your spreadsheet in a way that makes it easy. So if I get a new project and I think, wow, this is just like this project I did last year, and I can pull that old calculation, plug in new values for my new project, and I'm done. So that can save a lot of time and really can produce some rough savings numbers very, very quickly once you have a repertoire of bin calcs at your disposal to use. And maybe you might need to make some changes, but maybe you're not having to reinvent the wheel every time a calculation is needed. Some downsides, though, they are not useful for things which are not predictive by other variables. You have to be able to have some variable that can be used to predict power and energy use. And it can't tell you what that system is doing at a particular hour of a particular day. So if you do this calculation and somebody asks, well, what's it doing at 5 p.m. on January 5th? This data can't tell you that because the bin calc has no sense of time. All it tells you is how many hours a year are in each of those operating conditions. But that does not break it up into months and days and time of day. You can't use these for anything which has a time delay. So one example that I've heard in several instances, if you have a large concrete building, concrete is actually a pretty good thermal battery. And so if you heat up your building, that concrete absorbs that heat and acts as a thermal battery. And then when your heating system turns off, let's say it turns off for the night or the weekend because everybody left. What will happen is that concrete will take a lot of time to dissipate and disperse that heat, which this can't really predict how that's going to work. A full building energy model simulation, assuming it's one of the better ones. Apologies if you can hear my neighbor's dog barking in the background. But again, there's no sense of time here. So that delay, the buildup of the heat in the concrete, we can't model that. And usually these are only looking at isolated systems. So we're not looking at the entire building. So it might be difficult to account for other systems which might be impacted by the changes to whatever system you are looking at. So in all those examples, we were looking at one air conditioner or one heater or one fan system. So understanding those interactive effects that we've been talking about all semester, what happens when I save energy on my fan system? Well, that has an impact on my heating and my cooling system. So understanding those interactive effects is a big deal. If you're dealing with an existing building and the customer gives you monthly energy use data, so you can actually see what this customer was using month to month on their electricity, on their gas, you can't calibrate your baseline to match that monthly bills because, again, we have no sense of time. So we don't know how much of that energy was used in January versus February versus March. And we're typically only looking at isolated systems. Usually they're not sub-metered. So when you walk into a building and you're looking at a big fan that you want to model, chances are that fan does not have a sub-meter on it that is measuring the energy use of that specific fan. Normally, it's the entire building that's metered. And so if you know this building is using 200,000 kilowatt hours per year, you don't know exactly where that's all going. So you need lots of sanity checks, or what I call sniff tests. Is this a load of bull? To make sure your results are reasonable. A really obvious example, let's say you run through a calculation and you think this fan is using 75,000 kilowatt hours per year. But then the customer says, well, my whole building only uses 60,000 kilowatt hours per year. Well, that is a giant red flag, because your baseline for that one fan system can't exceed the total building use. So something is obviously wrong. So that would be an obvious red flag, but it could be, well, what if you run through your baseline calculation and you come up with 40,000 kilowatt hours? Well, that's less than the total building energy use, but that's still 2/3 of it. Is that one fan really using 2/3 of the electricity of this entire facility? Well, probably not. Maybe if it's a big specialized fan and that's virtually the only thing going on there, but generally that's not going to be the case. So it's extremely important to understand exactly how the system is operated, because we're not going to have all these checks and balances. You need to come up with your own reasonability. Is that a word? Reasonability tests to make sure that your calculation makes sense. So it's very important. Way back in module 3, I went over some Excel etiquette slides for what makes sense and what I expect on the Excel homeworks. So far, the Excel homeworks have been pretty minimal. We had some for the utilities module, but now we're going to have a lot of Excel work from here on out till the end of the class. So I'm going to re-upload that slide deck. So before you start these calcs, take a look at that. I'm not going to walk through this live, but I'm going to, last year I had actually recorded a separate standalone video walking through a very basic bin calculation. So in this case, we have what's called a makeup air unit, where you're bringing in outside air, no return air, just 100% outside air. We are either heating or cooling it to deliver 65 to 75 degree air. It's a pretty simple device. That's its one job, deliver 65 to 75 degree air. So if the air is coming in warmer than 75, it will cool it down. If it's coming in less than 65, it will heat it up. If it's somewhere in between, it'll just let it pass on through. And so this would be a bin calc, and I hope the resolution's coming through okay. But the high level walkthrough of this, I have my bins, my midpoint, my hours at each of those conditions, my fan power. In this case, my fan power is constant, so that one's pretty easy. And then I have my cooling energy, where it does a check. It looks at that outside air temp and says, well, if it's above some value, I need to cool it. And if it's below some value, I don't need to cool it. So you come up with the cooling power needed for each of those conditions. And then similarly on the heating side, for the required heating energy, it does a quick check. If my outside air temp is below a certain value, I need to heat, and comes up with that value. So I'll post that video. I think it's about 25 minutes, so I didn't want to walk through that live, but it would be good to just follow along and walk through. When you watch the video, make sure you up the YouTube resolution to the highest level it will let you, just to make sure that it comes through nice and clear. I got one more thing before we go, but any questions on bin calcs? All right. The other thing has nothing to do with this course, but I've done this every year, and the response has been good. I've had a lot of students say they appreciated this stuff. So I basically added it to the curriculum because the impression I've been given is that you as students don't really get a lot of help on the interview side and on the resume side of things. And I've sat through a whole lot of interviews. I've looked at a whole lot of resumes, and these are the tips that I've come up with. So real quick, is that still a true statement as far as there not being a lot of great support on this end of things from the
More or less
university?
so.
Sorry, what was that?
More or less so, for sure.
All right. Well, I hope this is helpful. Some resume tips. Have someone else look through your resume. Someone that you trust is going to put some time into it. The reason being, if the term I use is you will become numb. When you spend so much time poring over your own document, your eyes start to glaze over. You overlook dumb mistakes and spelling errors. And this still happens to me at work when I spend hours and hours on a drawing set for a design. And then late in the project, I'll just notice something so dumb or incorrect and just think, man, how did I overlook that? I've been looking at this drawing set for weeks. But it's true. You start to just sort of become numb to the stuff you create and pour all this time into. So have somebody else look at that resume. I'm willing to be that person. So if you want me to look at your resume, shoot me an email. I'll take a look and provide any commentary or anything worth noting. Try to make sure your formatting game is on point. Some recruiters or hiring managers are more attentive to this sort of thing, but those inconsistencies in your formatting, they just look sloppy. Engineering it's a very detail oriented field. One of the biggest things that I look for if I'm interviewing somebody is attention to detail. That's huge, at least in my industry, maybe less so in others. So for a real pedantic example, so in this case, this person, they had spaces on either side of that hyphen. Elsewhere, they didn't. And across this document, these are from the same resume, it just kept going back and forth. There was no consistency to it. It was all over the place. So like I said, that's a little pedantic, but I guess I noticed it, so others might as well. What's a little more glaring is spelling mistakes, experiments. That just looks really sloppy. So have somebody look at your resume. Cover letters. I always hated writing cover letters, but they are important. Make sure your cover letter is actually tailored to the company you're writing to. If you write generic cover letters where it's obvious you just changed the name of the company on the top, that is super obvious. And it goes straight into the round file, aka the garbage. I can notice immediately when a cover letter is just generic. There's no substance to generic cover letters. So write something that's tailored to the company you're writing to. Now, parts of your cover letter can be the same between companies, especially if it's part that's talking about yourself, because that's not really going to change for the different companies you're looking at. But there should be some section in there that when I read that, I think, okay, this is obviously talking about McKinstry and nobody else. So how did you find out about the company? Who did you talk to? Maybe you talked to me at the career fair. Is there anything about the company that really resonates with your background or something you enjoy? Or maybe it's a very progressive company and that really speaks to you. Maybe it's you're all about sustainability, that sort of thing. And you can similarly consider tailoring your resume a bit for specific jobs. You might have some classes or experience that might resonate a little bit more with different industries. If you're going into the HVAC field, well, obviously, HVAC design and energy auditing should probably be near the top of your class list, especially if you are listing 15 to 20 classes under your relevant coursework, which I've seen that time and time again. That doesn't really tell me a whole lot because I know all Gonzaga mechanical engineering students largely take the same courses. Doesn't necessarily hurt, but you can consider reorganizing that list a bit depending on where your resume is going. I'd be very careful going over one page on your resume. At this stage, I would be pretty shocked if any of you had enough experience to warrant more than one page on your resume. References, though, as a second page, that is fine. But the resume proper, where you're talking about your education and your work experience, that should just be one page. If you're getting to 2 pages, you probably have some fluff on there that maybe doesn't need to be there. Today, so I'm, let's see, coming up on 13 years in the industry. My resume today is still one page. Now, granted, I've only been at a handful of companies. If I had bounced around a lot more and had been at 5 or 6 different companies over those 13 years, maybe that might have pushed me to 2 pages. Work experience is most important, but the big caveat, especially at your stage, is a lot of you don't have it. I know that internships right now are super competitive, and I've met a lot of rock star senior engineering students who have yet to get their foot in the door with an internship. So sometimes you just don't have it. If you don't have the work experience, then I'd say list your education first. That's fine too. As you get more experience, that work experience should move to the top. But right out of college, it's not surprising at all to see education listed first. And if you don't have any of that work experience, expect that somebody might ask you about it. So if I had a senior engineering student who wanted an internship and it was their first one, I might ask them, well, I see you didn't have an internship your sophomore or junior year. Can you tell me about what happened there, or were you going for internships, just to start a discussion. If you have extracurricular stuff, that typically comes after work and education. You should be going from most recent to least recent in all of these categories. That's just a general rule. Depending on your overall GPA, I go back and forth on this one. I've seen a lot of resumes where the student will specifically list their engineering GPA, which to me tells me, well, maybe you didn't do so hot in your religion and philosophy classes, which I can certainly be sympathetic to. Those were, when I was going to Gonzaga, those were my lower priority classes, and I didn't do as well in religion and philosophy, but I did a lot better on the engineering side. Wherever possible, list some specific accomplishments and deliverables that you specifically were responsible for. As an example, a lot of you are listing your senior design project on your resumes. At least that's my guess. If you had a specific role on that team, maybe you were in charge of all the SolidWorks modeling, or maybe you were the one in charge of the machine shop work, and you were actually the one on the lathe making the parts and pieces. List those specific accomplishments. There was one example. We had a student a couple years back who had applied for an internship, and on her resume, she had listed that she was in SWE, the Society of Women Engineers. I think that's the right name. And she had that on her resume, and we asked about it, and we asked about her involvement, and it basically came down to she occasionally went to a meeting sometimes, and that wasn't really a good look. It would have just been better to not list it. But the bottom line is she didn't have any specific contributions with that group. She just kind of went there from time to time. So assume you're going to be asked about those things. That's a common interview question for me. If I see a senior design project listed on your resume, I'll often ask, what was your role? You know, some people really like getting into the nitty gritty in SolidWorks. Some people like to play more of a project manager role, or some people just love the presentation side of things. It's just to kind of gauge where your strengths are. One question that comes up a lot: do you list hobbies on your resume? And I don't have a solid answer for this. Me personally, I like to see hobbies because I like to see who this person is outside of the job, and then think about, well, how might this person fit in with the culture of the company and with the immediate people that they're going to be working with every single day. So I personally like it. Others might say to leave it out. By listing that, you might make a connection with the person interviewing you. So, oh yeah, oh, you play ultimate frisbee? Yeah, me too. And then we can have 5-minute discussion about ultimate frisbee, and I'm going to leave feeling pretty good about you. Or, hey, you're really into scotch. Do you prefer Highland, Speyside, or Islay scotches? Maybe don't go with that example, but just to illustrate an idea. If you have a hobby that's professionally relevant, so a common one might be you coach for a kid's team, little league baseball or soccer or something. Yes, that's a hobby, but that also shows some volunteer work as well as some leadership skills. So that would be a pretty great thing to list on your resume. But if it's not professionally relevant, then you might need to read the company a little bit, i.e., if you got a small engineering firm, everyone's wearing jeans, seems like the atmosphere is pretty casual, then you're probably going to be okay listing something like that. But if it's a super professional company, everyone's wearing ties, nobody's smiling or laughing, maybe you don't want to work there to begin with, but maybe they'd be less receptive to having hobbies listed on a resume. But regardless of which way you go, it shouldn't take up a lot of space. If you don't have other stuff to put on your resume, don't just fill it with hobbies, because that's not good either. So that's some resume tips. Some interview tips. If you can find who you're interviewing with, which they should be able to tell you that. They might not tell you um, without you asking, but if you ask the question, you should be able to get some names for who you're going to interview with. And it's a good idea to connect with them on LinkedIn before the interview. You don't have to start a conversation or anything like that, but just connect with them, and then they can pull up your profile, say, "Oh yeah, this person's done this and that, and oh, that's pretty cool." Always do some homework on the company, and please prepare a list of questions beforehand. So some common ones. Describe a typical workday for someone like me. How many engineers are on staff, or how many would I be working with on a regular basis? Who would I be reporting to day to day? Where are your projects? Am I going to be traveling across the country, or am I going to be staying in Spokane all the time? How often might you be talking with people in other offices? What's the typical career path? Where am I going to be in, say, 5 years? What kind of progression is there? Are your engineers encouraged to get their license or other continuing education? And you are going to want to look up some of the generic common interview questions and prepare some answers ahead of time, because you don't want them to ask you those questions and then have you sit for a minute thinking and then say, I don't know. That's not a good look. So some of the common ones: describe a time when you had to mediate conflict. What's one of your weaknesses? What attracted you to this company? What attracts you to this field of work? What's your greatest accomplishment? So these are highly generic questions that any company could ask you. And a lot of, especially if the company has people in the HR department, because those people are generally not engineers. And so they don't really ask engineering questions. They ask you these kinds of questions. And I hate these questions. Absolutely despise them. If I'm interviewing someone, I don't ask these kinds of questions because I got better things on my mind. But especially if you're interviewing with somebody from the HR department, expect these to come up, and try to think of an example that you could bring up. But try not to feel like you're reading from a script, which can be tough. Important to send a thank you letter, note, email to whoever you interviewed with. Maybe you do it a day or two later, and that'll kind of serve as a reminder that, hey, thanks for your time. Excited to hear more about the opportunity. Maybe you have a follow-up question you want to ask. You might have to call the front desk of the company to get their contact info, though. Or another sneaky way to do it is during the interview, you ask them for their business card. And lastly, now that I've told you my expert opinion and given you all the right answers on how to nail your first job out of college, take it all with a grain of salt. So everything I said about resumes, as far as how I think you should do these things, it's completely subjective at the end of the day. There is no absolute right answer. There's very few hard rules. This is my personal experience, and I hope it's helpful, or at least giving you something to think about. Um, so yeah, that is all I got for today. Any questions on this or anything else? All right, I will stick around for 15 minutes or so if anyone's got homework questions. Otherwise, Have a good weekend, and I'll see you Tuesday.